So I think my screen is visible to you, and am I audible to you? Okay, so good evening, everyone, and I'm Kamla Mishra from IIT Mandi, and I'm here as your TA guide for the course Probability and Statistics, uh, which is introduced by the instructor Professor Somesh Kumar from IIT Kharagpur, and this is week 9 of problem solving session. So this week the course is basically about the parameter estimation. So it's about it's about parameter estimation. So now the firstly we will say that what are the kinds of parameters. Okay, so if there is any random variable which follows some distribution, then let's say x follows normal distribution. Okay, so mu and sigma square, these are the parameters of that distribution which x follows. So mu and sigma square is parameter. So to find those parameters we have some techniques. Now before going to that, we need to understand that if we have a estimator, then uh, whether it is really estimating, like whether we can really believe on that, rely on that parameter, so that sample parameter, so that we can have the information regarding this uh, population. Okay, so to get that, what we do is that we have some estimator, and then we check whether these are unbiased estimator. So whether in, like, it does not happen that one time this is expectation is equal to mu, one time it's not equal to mu, it is some less than mu or greater than mu. So this is uh, what we call is unbiased estimator. Next we check whether it is consistent or not. So it should not happen that we are some, like it uh, I will tell you the definition. It will be something like in the form of probability. So when n tends to infinity, the probability that estimator is equal to a real estimator should be like very equal. So equality should be equal to 1. So the probability that it is greater than some any real value, any small real value, goes to 0 as n tends to infinity. That means the parameter needs to be consistent always. It should not happen that when we are increasing the number of samples, then it is changing. Okay. So these are called basically point estimators. And another thing we have is that interval estimation estimator. So first we have point estimator, and second we have interval estimation. So as per the name suggested, in the time of point estimation, what happens is that we have one point. So one point clarifies whether this is, let's say, the mu value of our population is that 5. Okay, and then we are checking it is as 4.9 for the sample. Then in the point estimation, what we do is that we just reject this, okay, because it is not equal to 5. But in the interval estimation, what we say is that there can be some error. So we take some kind of interval. So let's say I am telling you that, okay, uh, as like population is, let's say, 1 lakh, and then we have sample size of just 1000, and then we want to check 1000, we want to know the information regarding the 1 lakh just by having 1000 sample. So we can say that, okay, I'm okay with this much percentage of error. So then we say the confidence interval, and regarding that we find this interval estimation. So if I say that, okay, zero point 0.2 error we can permit, so then it range will be 4.8 to 5.2. Then this will come in this range, and then we say, okay, we can estimate it by this value also. So this is what happens is that it depends on you how much the estimation you want to take, what is the interval you can permit here, or if you want very very exact result, which in the reality does not happen generally, so then at that point of time we use point estimation. Okay. So if you have any question, any doubts, you can just ask me in the middle. It's fine, totally fine. Okay. Okay. So next thing is that first we have unbiased estimation. So if you have gone through the slides, it is very good that you may know these things already. If you have not gone through the slides already, so this is just an overview kind of thing, so that whatsoever questions we are going to do here in this class, you will understand that. Otherwise it would be so difficult if you don't know this basic things regarding this estimations and all. Okay. So what happens is that we take one this statistic. We take one statistic. Let's say it contains this x1, x2 up to xn. This is any random variable which follows some kind of distribution, and then we denote it like this. So we say this is unbiased estimator of g theta if e of tx is equal to g theta. Okay. So if expectation of that unbiased, if expectation of that estimator is equal to that parameter, okay. So let's say we have some x bar, and then let's say t is equal to x bar, then expectation of x bar is equal to uh, in case of, let's say, xi, all xi follows normal random variable mu and sigma square. So x1 x2 up to xn all follows this normal random variable. So what happens is that for everyone the mean is mu. So the summation divided by n that also have mean mu, so this is equal to mu. This g theta is the parameter, so this is g theta here. Okay. So what we are saying is that we are checking for this here theta, or g theta, whatsoever it is. This is the function of mu. So this is what we call as unbiased estimator. So this is just an example. Okay. And then if we have, let's say, e of tx bar is equal to some g theta plus b theta. Okay. G theta plus b theta means, yeah, an issue. Is there any issue? So now what we know is that we have this parameter. This was for, we were checking for this parameter. Let's say mu in the case of a normal distribution, or maybe lambda in case of Poisson distribution, or etc. Like there are so many. So this is just an example. So if we have one extra term like b theta, what we say is that bias. So this is biased estimator. If this is not equal to this, if b, and here of course b theta not equal to 0. So this is we call how much biased this estimator is. So if we go through this slide where I have said that our mu is 5 and sample mu is 4.9, so this is biased by zero point 0.1. So it does not matter whether it is negative or positive, so it is biased by a zero point 0.1. So then it will depend whether we want to select it or not. So this is the biasness of this parameter. If this is equal to 0, then we say it is unbiased estimator. Otherwise it is biased estimator. So this is the first thing we check in the time we do the estimate. We select the estimator to get the information about our real distribution. Next thing what we check is that is consistency. Consistency. So for consistency, what is needed? Again, we have g theta parameter. So we are checking the consistency of our parameter which we are choosing according to this. So whether that parameter is consistent for this real parameter, or maybe you can say that population value. So this happen is that if for every epsilon greater than 0, p of tn minus g theta r, this needs to be greater than epsilon goes to 0 as n tends to infinity. Okay. Now, what does this mean exactly? So, let's say we have x1 up to xn. Okay. This is the number of sample. Let's say we have n number of sample, and then we have this parameter tn. Okay. So, that time the parameter is equal to this gn theta. Uh, it has greater than epsilon, probability goes to 0. What it means is that if we just do opposite of this, let's say tn minus gn theta, okay, less than epsilon, what it will be? It will be just 1 minus this. Okay, probability of something greater than epsilon, if it goes to 0, then less than epsilon it goes to 1. Less than epsilon goes to 1 means if we have gn theta here, okay, and then tn theta here, let's say at n is equal to 20. Okay, so as n tends to infinity, this Tn is approaching to Gn theta. So this is, let's say, Gn theta and this is Tn. So what we are saying is that as we increase the number of samples, as we increase n, this Gn theta tends, this Tn tends to Gn theta, and its probability uh, is approaching to 1. Okay, so let's say when n is equal to 20, the probability that this value is less than very small value, let's say 0.05, epsilon means epsilon is very small value. So that's why we say for every epsilon greater than 0, every epsilon greater than 0 means if we have this 0, then epsilon can be anything. It can be 10 to the power minus 10. So this is very small value. It's like kind of negligible. So that means that the probability that Tn is equal to Gn theta and as n tends to infinity should be equal to 1. So we do not directly write it as equal to 1 because n tending to infinity to, so we have nothing like n is equal to infinity. So as n approach to infinity, the probability also approach to 1. So this probability approach to 1, that means this probability approach to 0. So this is how we define it. But the meaning to understand is this, that as we increase this n, this Tn will converge to this value. It should not happen that we are increasing the n and sometimes Tn is going here, sometimes Tn is going here, sometimes Tn is going here. It should not happen. It should happen in this way that Tn converges to this Gn theta. Okay. So I hope this is making sense to you. Okay. So next, what we need to know is that okay, these are the things we can check when we have estimator. But what if we do not have any estimator? We just have some data or some points. Then how do we find these estimators? So that time, what we have is that we have some techniques. Basically, least square estimation, and then method of movements, and then estimation. And then what we have, this is not how to find this estimation. This is uh, mean square error criterion. So this is not to find the estimation. This is to find the error between the estimator we have and the error between the real parameter we have. So something like this. So if you go here, then this biasness, whatsoever this biasness we have, this will come under mean square estimation. So we calculate this biasness in different form, but this is what we want to know, is that how much bias is this and can we then accept that biasness or not. So that is criterion. So criterion means we have some criteria that if uh, it, it lies in this criterion, then we accept it, and otherwise we reject it, that we cannot accept this much kind of biasness because it is not actually giving the information about the population, but it is kind of giving the misleading results. So that means that if we have too much biasness, then it may mislead the results. So we say that okay, we are not going to use this estimator. So for this we use mean square error estimation. Okay, so now and the most important one is this maximum likelihood estimation. So method of movements we use very rare least square estimation, but then the most used is that maximum likelihood estimation, and then we found its estimator and we say it as MLE. Okay. Okay, so maximum likelihood estimation is uh, sorry, so the least square estimation is basically, let's say we have some points and number of points x1 x2 up to xn yn. Then what we have is that, let's say yi is alpha I, sorry, alpha plus beta xi plus epsilon I. Now this epsilon I is what? Error. Okay. So least square estimation means what we want to do is that we want to minimize this error. Okay. So if we minimize this error, this yi, if we want to estimate by xi, then it will be let's say error is 0, then we have found the best fit. Okay, so this is least square. So least is square error. So if is square and then this one, and then we want to just minimize this error. So this error we can further write it in the form yi minus alpha I minus beta xi whole square. Okay. So now to do the minimization and all, so to do minimization, what we do is that del s del alpha is equal to 0, and then del s del beta is equal to 0, because alpha and beta there are two parameters, right, which are connected. Now if you solve these things, you will find uh, that means like these all things are already in lecture, so I'm just gonna tell you the answers only. So yeah, so beta cap you find is that beta cap means this is the parameter estimator. Okay, is syx, which is uh, covariance. Okay, so why we write s, because it is for coming from the sample, and then alpha cap is that y bar minus beta cap x bar. Okay, so these are alpha and beta. So alpha and beta, after that what we do is that we find whether these are biased or unbiased. So these are the unbiased parameter. So in after you do this expectation of alpha cap and then expectation of beta cap, and then you put in the value and then you solve, you go through all these things, then you will find that these are basically unbiased estimator, which you have found here. So this is the whole process of basically doing the least square estimation. So in case you ever want to find how to uh, the question is that you need to find the least square estimator, then you can find it this way. Okay. So if you just want to know like a lot about this thing, if you want to go in depth, then just go through the lectures. So of course you will go through the lectures to solve this, but this is just basic idea. So this class is okay. So now is what is called method of movements. So this is what we call, we have some expectation, like let's say we have some x1 x2 up to xn, and it follows some distribution p theta cap, and theta cap means some, let's say theta 1 theta 2 up to theta k. these are what estimators. So if you have Poisson distribution, you have just one estimator lambda. If you have exponential, you have one estimator lambda. If you have binomial, you have two estimator, which is n number, and then p as probability of the getting the truth value, or getting this whatsoever is the case. Okay. So depending on the distribution, this theta, this parameter will change, but overall uh, this is parameters. Let's say we have k number of parameters for any kind of distribution. So what we have is that we have mu1 dash, okay, is equal to some g1 theta 1 up to theta k, and similarly for this also we have some. So these are nothing but the form of functions. Okay, so if you have let's say normal distribution, so this is the one kind of what to say, this is mu, not sorry, this is not mu, this is, you have mu and sigma square, so this is some kind of function of mu and sigma square, this is also some kind of function of mu and sigma square, and this is, let's say you have moments. So what you do is that we find the theta I in is equal to some h mu1 cap up to mu k cap. Okay, so then we find these estimate, these in the form of the estimator, theta I in the form of these estimator. So this is a method of moments. Okay, so in the method of moments, we estimate these theta I with the help of these moments. So of course, when we will solve the question, it will be much more clear. This is just how we use method of moments. Now, next is that maximum likelihood estimation, or maximum likelihood estimator, which we say MLE. So MLE is basically what we consider that x1, x2, okay, up to xn is coming from a population which have PDF defined. Okay, so this is very important that we are considering here PDF. In the previous one, we are just considering this is coming from the distribution, and anyway that time also you can find the PDF, but here we are directly considering the PDF, and this is x. Okay, so x is the random variable, and theta r is the parameters. So you can have the parameters depending on the distribution again. Okay, so now the joint PDF, if we say for n samples, this is x1, x2 up to xn. Okay, so all are random variable and all are independent variable. So what we have, the joint distribution is what we know, that if x1 up to xn are independently and identically distributed random variable in any parameter, then its joint distribution is what? Anybody wants to answer this? Let's say we have n random variable, and then these are identically and independently distributed, then what is its joint distribution? Okay, so the joint density function, joint density function, not distribution. The joint density function is given by the product of these density function. So this will be product uh, over I, let's say I from 1 to n, fx I theta. Okay, so this, what we call is that g L theta bar x bar, and then we take log of this. Okay, so why do we take log? So that multiplication sign will basically goes to summation, and then it will be easy to take this uh, uh, s- sorry, it will be easy to do the differentiation, because in the multiplication differentiation can be much difficult. Okay, so then we say is that L is equal to log of L. So the definition is that if a statistic theta bar x bar uh, is said to be MLE. Yeah, by the way, this function, what we say is that likelihood function. Okay, if L of theta cap x bar, sorry, is greater than or equal to L theta. So basically, what we are doing is that what we are saying is that this is MLE, maximum likelihood estimator, if its likelihood is greater than or equal to the likelihood for of this for all the theta belongs to parameter. Okay, so for all the theta belongs to the parameter value. What does this mean is that we from the uh, sorry, from the name itself we can understand this maximum likelihood estimator. That means likelihood we have, like we have likelihood function, and then what we want to find is that it's maximum. That means we want to maximize it. So what we do is that we have L is equal to log L. Okay, let's say one equation. Then what we do is that we just do its differentiation with respect to all the theta i's. Let's say theta 1, theta 2, theta 3, and then we say it is equal to 0. Then at which point it will maximize? It will maximize when del 2 del theta I2 will be less than 0. So if this condition satisfy, then we have found already our maximum likelihood estimator. Okay. So then that estimator will be named as maximum likelihood estimator. Now, one more thing we need to understand is that sometimes what happens is that we have found some estimator, but then it is not in the range. Okay, let's say we have uh, uh, let's say we have any distribution, and for this we have x greater than theta, and then we have found theta value something which is greater than x. So this is not a possible thing. Okay, so that time we say that this is not maximum likelihood estimated, and then we do something else. We either take x1 xi, and then either we take this one, or either we take the opposite one. Okay, so x1 x2 are the minimum value that we will discuss. Now, the last one is that mean squared error criterion. Mean squared error criterion means what? You have, let's say, let's say t1. Okay, so mean squared error means how much error this estimator have. So if you have MSE of T1 is greater than MSE of T2, then what do you think? Which one is the better estimator? Estimator T1 or T2? Just on the basis of the things I have told you till now. MSE, okay? MSE means error. Error means T1 is how much deviating from the real value, and T2 is deviating from the real value. This is, let's say, error. Then which one do you think is a better estimator, T1 or T2? So I'm giving you 1 minute to think, and then I'll tell you the answer. Any guesses at least? Or maybe you can write in message also. I'll check it. Okay, so as you can see that error in T2 is less than error in T1. So T2 is the better estimator. Okay, so then uh, how do we find this mean squared error? Okay, so firstly we will take, let's say we have the real estimator as T. Okay, this is T2. So mean squared error. This is the mean. This is a square. This is so expectation of this one and then a square of it. This why that is how we can find this. Now the last thing I need to discuss in this class theoretically is order statistics. Order statistics. So that is, I think, uh, that is that you need to go through here also, because in the lectures also I have seen that it is not given very clearly, and then to solve the problems you may need to go through all these order statistics. So you will need to remember everything, but then you need to understand how we are finding this order statistics. Okay, so this is with the examples I'm gonna just teach from here. So this is, let's say you have just some sample discrete samples. So 6938. So what we do is that we are just arranging it. So it will be 3689. So 3689. So x1, this is first order statistic or smallest order statistic. This one is minimum of the sample. So minimum of the sample x1 xn. So here x1, this x1 is equal to what? This is 3. So this x1 is basically equal to x3. So x bracket 1 is equal to x3. This is the minimum. And this one is xn is maximum. So maximum is lying at 9. So this capital X4, which is maximum, is basically is equal to small x2. So this is how we find this order statistics, but this is the formula. Okay, so if you can see the arrow, I'm pointing it here. So this is the formula fxrx. This is equal to this value. This is for what? Uh, I think this is for all the distribution. Yeah, this is for the density function. So this is for the density function. And if you have discrete value, you can just find it by this method. So this is the order statistics, and then you have different. So order statistics sample from uniform distribution. So if you have uniform distribution following some kind of distribution, then generally what you have for uh, if you have uniform distribution, fx is what? You have 1 upon b minus a. Okay. If uh, x follows u a comma b. Okay. Right? This is how you have find fx, f is small x. But then here for uniform distribution, this is how you treat u of k. So this is minimum. So this is fx, but then you have fx of kind of something like this. Let's say x at 1, x at 2. So we symbolize it as fxn. So then this will follow a different kind of distribution. So f of uk will follow a different kind of distribution, and this is given by this parameter. So it is beta k. Basically, this is what we say beta kn plus 1 minus k. This is the beta distribution. If you go through the previous lecture, you may remember, or if you have already remembered, it's very nice. So this is for uniform distribution, and then for exponential distribution. So you can find it on your own also. It's not a big deal. You can just what you need to do is that just go here, and now for for uniform distribution, you know small fx is this 1 upon b minus a. Capital fx, you also know t minus a divided by b minus a. Okay. So or if you are taking x, so x minus a divided by b minus a. So you can just put this value here, this value here, and this value here. If you put all these value here, you can find this order statistic for that kind of distribution. So similarly for the exponential distribution you can find, and then I think these, then Erlang distribution or gamma distribution you can find. So these are some example. You can do it here, and then you can do it on your own also. So these are the basic things we needed for this class. So okay, now we will go to the questions. So what is given here is that x1, x2. Okay, just a minute. Okay. What's given here is that x1, x2 up to xm be the random sample from Poisson distribution. So Poisson distribution we know with the parameter lambda. Okay. So which of the following is unbiased estimator of lambda? So now you know expectation of xi is equal to what? For lambda, I think for lambda you know the sorry, this if you have Poisson distribution, this lambda is equal to mean, right? This estimator is equal to mean. So if you have expectation of xi is equal to lambda, what will happen is that expectation of uh, x bar, which will be equal to x1 plus x2 up to xn divided, sorry, m divided by m will be equal to what? 1 upon m, and then for each xi it is lambda, so it will be lambda times m, right? This one lambda, 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 so it will be lambda times m, and m will be cancelled out. It is equal to lambda. So expectation of this x bar is what? You unbiased estimator. So x bar we have as estimator, its expectation is equal to the parameter itself, lambda. So what we say is that yes, x bar is unbiased parameter of lambda. Now, next we need to find is that expectation of s square. So, then, well, these are the known results, but then, okay, still we can solve. So, expectation of s square is what? Is it is basically 1 upon n minus 1. S square is sample variance. How do we define this? This is 1 upon n minus 1. Okay. And then xi minus x bar whole square. So this is sorry, xi minus x bar whole square. So what we can do is that we can open it either 1 upon n minus 1, and then it will be summation xi square, and then expectation of xi square minus expectation of x bar square. So then you need to go through what is the expectation of xi square. So this is lambda. Okay. So variance is also lambda. Variance of xi will also be lambda in the term of Poisson distribution. So what we have is that expectation of xi square is equal to what? Lambda plus lambda square, I think. Okay, because it will be what? Variance of xi is equal to what? Expectation of xi square minus expectation of x bar whole square. So it will be lambda plus lambda square. So then you need to go through here. You can put 1 upon n minus 1. Let's just write it down here. 1 upon n minus 1 here, right? This is, and then expectation of summation xi minus x bar whole square. Okay, so that you can write it as 1 upon n minus 1 expectation of summation xi square, okay, minus expectation of x bar whole square, sorry, plus and minus 2 expectation of xi, sorry, x bar xi. Okay. So expectation of xi will be also equal to x bar, and then this and this will be cancelled out. So this will be 1 upon n minus 1, and then that will be lambda plus lambda square n times minus uh, summation will come over everything. So let's just not take here. So 1 minus lambda square will cancel out, and lambda square, and okay, something like that. I don't remember exactly the proof of this, but this comes as lambda. So I will just go through this. So this is also the unbiased estimator of uh, what do we say? Lambda. And then we check for this. So x and s square we all know. So it may be a or b. Okay. So The formula is alpha x bar plus 1 minus alpha s square. So its expectation will be what? It will be alpha of expectation of x bar will be lambda plus 1 minus alpha. This one will be lambda, so it will be lambda only. So this will come as lambda. So basically, these are the answer. Okay. So unbiased estimator are this and this and this. So you can also remember if you have one unbiased estimator and you have second unbiased estimator, then what's if you then alpha times first estimator plus 1 minus alpha. That means basically 1 minus alpha plus alpha. This value needs to be is equal to 1. So if this is 1, then any combination of it will also be the unbiased estimator if both of them are unbiased estimator of its proof. I will just write it down and then you can go through the slides. Now the next one is that which of the following is unbiased estimator of sigma square. Okay. So unbiased estimator of sigma square uh, will be what? So the given thing is that it is coming from the population which is which is following the normal distribution. Okay. So if we take s square as this, uh, 20 s1 square plus 10 s2 square plus 8 s3 square divided by 38. Then expectation of s square will be what? 20. Expectation of s1 square will be so 1 upon 38. We will take firstly common. It will be sigma square plus 10 sigma square plus 8 sigma square. So the overall it will be what? 20 plus 10 plus 8, it will be 38 by 38 sigma square. So it is sigma square. So this one will be the answer. Now, third is what? X1 up to Xn are the random sample from gamma distribution. Okay. So, gamma distribution is what? Gamma distribution have parameters lambda and r. Xi distribution from I to n. Okay. So, we want to find the moment estimator. Moment estimator means what? We want to find the estimator with the help of method of moments. In case anybody has any doubt, you can ask me, okay, or you can write in the chat box. Right now, there is no issue. Good. So, the method of movements is that we have firstly mu1 and then mu2. So mean we know here is that mean is given by r upon lambda, which we can write is as mu1 cap, and then mu2 cap, which is xi square. So 1 upon n summation xi square. This is what? 1 upon n summation xi, right? This is mu2 cap, and this is what? r r plus 1 divided by lambda square. Okay. So then mu1 mu2. So we have mu1 cap mu2 cap. We have two equations, and then we want to find this r and lambda in terms of mu1 and mu2. So this is what we call this method of movement. So we have two movements. We have first movement as r upon lambda. We have second movement as r into r plus 1 divided by lambda square. With the help of these two movements, we want to find this estimator of moment estimator of lambda and r. Okay. So now what we need to do is that we need to solve this and this equation so that we can find the answer in terms of mu2 cap. Now what we can write is that mu2 cap, we can write it as r square upon lambda square 1 plus 1 upon r. So basically we are taking r common from here. It will be r square. It will be 1 plus 1 upon r. Uh, r. Sorry. So r square upon lambda square is what? Mu1 cap square. So this is mu1 cap square 1 plus 1 upon r. Now you have only r here. So it will be what? Mu2 cap minus mu1 cap square is equal to, sorry, mu2 cap divided by mu1 cap square minus 1 is equal to 1 upon r. So r will be what? Reciprocal of it. So r will be 1 upon 1 minus mu2 cap divided by mu1 cap square. So um, there is something wrong. Yeah. So it will be, it should be like this. So this is what mu1 cap square will go to upside. Okay, mu1 cap square, and then this one will be what? Mu2 cap minus mu1 cap square. Now this is what? Expectation of x square minus expectation of x whole square. So this is variance. Okay, so this is variance, and this is what? Uh, this is x bar. So this is x bar square. So then r we can write it as x bar square divided by the variance. How we can write variance? We can write it as 1 upon n xi square minus x bar square. So then we can write variance as summation xi square minus x bar square. Okay. So this one can be r. Anyway, we will solve. So this one is x bar square. This one is 1 upon n summation xi square. This one is x bar square. Now next, this is r. So lambda is what? We have r upon lambda is equal to mu. So r upon lambda is equal to mu1 cap. So r is mu1 cap whole square divided by mu2 cap minus mu1 cap square 1 upon lambda is equal to mu1 cap. So mu1 will be cancelled out. Lambda will be mu1 cap divided by mu2 cap minus mu1 cap square. Okay. So mu1 cap is what? X bar. So this is x bar minus 1 upon n summation xi square minus x bar whole square. So this is the parameter estimated for lambda, and this one is for where? This one is for r, right? So this is the answer. So these are the parameter estimated for r and lambda. So I hope you are getting all these things. Now the next question is that we want to find the MLE. MLE of theta, where theta is coming from what? Normal distribution. Okay. So to find the MLE, what we do is that firstly, with the help of fx theta, what we create is that likelihood function. So firstly, we create likelihood function, and then what we do is that we do the multiplication of it, and then we find this normal distribute. We find this maximum likelihood estimate. So first thing given here is that x1 x2 to xn follows normal theta. So theta is mu and sigma squares. Now what will be its distribution? Let's say xi. So it will be 1 upon under root 2 pi. Sigma is 1. Expectation of xi minus mu. Mu is what? Theta square divided by 2. Right? So this is what we say fxi. Now likelihood function L x theta is what? So mu here is theta, so we can just directly write theta here. And then if you have more than one parameters, then you can write some mu and sigma square. So this is what multiplication of this. Multiplication I 1 to up to n random samples given. So 1 to up to n 1 upon root 2 pi expectation of minus xi minus theta whole square divided by 2. Now you can understand from here is that it is if you just go through this, it is quite difficult to do the integration from here. Okay. Now, okay. So this is basically what multiplication. So if you do the multiplication n times for this, so its value will be what? 2 pi to the power n upon 2. Right? 1 upon 2 we have already. So we are just powering it n times. We are just multiplying it n times. It will be 1 upon 2 pi to the power n upon 2. Now this is expectation of xi minus theta square. So you have if you have expectation of minus ax, expectation of minus bx, it is what? Expectation of minus a plus bx, right? You know this thing. So if we are multiplying all these expectation, then what happens is that it will automatically come as summation here. Are you getting this? Is this understood? Why we are writing it in this way? Okay. So then what we do is that we will find the log and then we represent it as a small l. So log of L will be is equal to what? It will be is equal to it will be is equal to what? N by 2, and then uh, if you take the log, so log of a times b is what? Log of a log of b. Okay, so for the first time I'm writing this whole, and for the next time you can understand it on your own. So this is what? Log of 1 upon 2 pi and by 2 e to the power minus xi minus theta whole square to summation over I. Okay. Now log of a times b is log of a plus log of b, and log of 1 upon a is what? Minus log a, right? So this value will be come out as minus n upon 2 log 2 pi. So in case you have not understood how this is coming, you can ask me. Otherwise, I will think that you have understood it. So I'm not gonna say it by just solving the whole thing. So this one will be what? E to the power. So log a to the power e will be what? Sorry, log e to the power a is what? A log e, and log e is 1. So that one will not come. So this will be your uh, log likelihood function. Okay. Now what we want to find is that maximum likelihood estimator, and to do that what we do is that del L del theta is equal to 0. Simple, right? So del L del theta is equal to 0 will be what? Here there is no theta. Here is the only part where is theta. So this one will be 0. This one will be what? Minus x square. Let's say theta is or y. What do you want to say? So theta is xi minus theta whole square. So it will just come out as what? Minus 2 summation xi minus theta square, and for minus it will come out as plus. Sorry, square will not come. So let's go. Right. So this will be what? Summation xi, and then if you summation do the summation for the theta n times, it will be n theta, which will be is equal to 0. So this will be your summation xi by n is equal to theta. So uh, theta mle is what? X bar. Sorry, just right, theta is equal to x bar right here. So now we have found theta is equal to x bar. Now it is also needed that we have found that this is the what do we say? This is less than 0, because then only this will come out as maximum likelihood estimator. So what we need to find is that del 2 L del theta 2. It will be what? It will be uh, so the L was 2 del L del theta was what? 2 del theta was xi minus theta. So del 2 del theta 2 will be what? Minus 1, right? Minus 1. So minus 1 is greater than 0. That means it is less than 0. So function is maximizing at this point. Now we can say that theta mle is x bar. So x bar will be the answer of this question. This will be the answer. Okay. Okay. Next, what we have is that mean square error. We want to find mean square error. So that I have told you how you have find it. You have this t as an estimator of mu, and then we want to find what is the mean square error. That means how much it is, this estimator is deviating from the real value of the mean of distribution, this exponential distribution. Now in the last class or maybe in the previous ones, I have told you that if xi follows exponential distribution with mean me, then summation xi, let's say denote it as, because we are using here summation xi, this follows gamma distribution. Gamma distribution with n 1 upon mu. Okay, so this follows gamma distribution with gamma n upon mu. So okay, so what do we have is it MSE of t. MSE means mean squared error. Okay, so in the mean square error there is not under root. Okay, this will not come because we are just taking the mean of squared error. So this is just mean square error. So here, okay, this will be mean square error will be what? T minus mu whole square. Right? So now T is what? 1 upon n plus 1 summation xi. Now this summation xi we can write it as y because now we know the distribution of y, so we can find its expectation directly. Right? So MSE of t will be what? It will be MSE of t will be what? It will be expectation. This one is y upon n plus 1 minus mu square. So this one I'm writing it as y. Y is equal to summation xi. Now it will be equal to what? Expectation of a minus b whole square just. So it will be expectation of y square divided by n plus 1 whole square. This is constant plus expectation of mu square minus 2 times expectation of mu is mu, and then it will be expectation of y and whole divided by n plus 1. Now previously we have just seen that expectation of y, where y is gamma distribution, it is r upon lambda. So here r r upon lambda. So r is n and lambda is 1 upon mu. So r upon lambda will be is equal to what? N mu, right? And then expectation of y square also we have seen is that r into r plus 1 divided by lambda square, right? So r is n, so it is n into n plus 1, and this one is mu square. Okay, so now we know this and then this. So expectation of y square is n into n plus 1 mu square divided by n plus 1 whole square, and then expectation of mu square will be mu square, expectation of y, so it is 2 mu n mu divided by n plus 1, right? So this n will be cancelled out, it will be uh, n mu square divided by n plus 1, it is minus 2 mu so this is n mu square, this is minus 2 n mu square divided by n plus 1, right? And then plus ka mu square. So it is n mu square divided by n plus 1 plus mu square, and then 1 minus will be cancelled out. So it will be minus n mu square plus n mu square plus mu square divided by n plus 1, right? So this and this will be cancelled out. So answer will be mu square divided by n plus 1. So this is the answer. So mu square divided by n plus 1 will be the answer. So this is the uh, mean squared error. So this is how much it is deviating from here. So next question is that what you have given is that x is a random variable with the distribution by Bernoulli random variable. Okay. So in Bernoulli random variable, what happens that if you have truth value, you have probability p. If you have false value, then you have probability 1 minus p. So what is given here is that if mu n denotes the nth moment about the mean and mu 2n plus 1 is equal to 0, if and only if the p value is this. So now I'm telling you the formula, but if you want to know more about this, then you can just go through the Bernoulli distribution. You can just search here for Bernoulli distribution, and here here you have the formula. This one is mu k. So at k you have the formula. So we are gonna apply this at mu 2n plus 1, right? So what is given here is that px is equal to 1 is equal to p, x is equal to 0, 1 minus p. These two things are given. And then mu 2n plus 1 is equal to 0. Then we want to find what is the value of p, right? So mu k is defined as 1 minus p to the power k plus p 1 minus p to the power k, right? So mu 2n plus 1 is equal to what? 1 minus p to the power 2n plus 1 plus p 1 minus p to the power 2n plus 1 is equal to 0, right? So then we can take just common. What we can do is that here we can take p common, right? So minus p to the power 2n will be the positive thing. So if we take one p common, it will come as negative here, right? And then 1 minus p we can take common also. So it will be minus p to the power 2n plus 1 minus p to the power 2n, because p we have taken out and 1 minus p, 1 power we have taken out. So we are left with power 2n, right? So now p is not equal to 0. 1 minus p will also not equal to 0, because if p not equal to 0, 1 minus p cannot be equal. That means if 1 minus p equal to 0, that means p is equal to 1. So p is neither 1 nor 0, that we know because of this condition where we have given p is in between 0 to 1. So p cannot be 0, cannot be 1. So this is not 0, we can divide this value. So we are left with this as is equal to 0. So minus p to the power 2n plus 1 minus p to the power 2n is equal to 0. What it means is that 1 minus p to the power 2n is equal to p to the power 2n. Now you can just remove this because power is same. So denominator, sorry, the this value will also be same, so it will be 1 is equal to 2p, so p is equal to half, right? So p is equal to half will be the answer. So next question given here is that which of the following here is a consistent estimator of mu? So consistent estimator of mu is that firstly we can check that whether it is unbiased or not. So if it is unbiased, then only it can be consistent. Otherwise, we can just remove that estimator at one point only. So now, if you have expectation of root x y, then we know that in general case it is not equal to expectation of root x expectation of root y, right? Um, and it is not equal to this expectation of root xy, right? So if you have expectation of this xi to the power 1 upon n, then this is not equal to expectation of xi this to the power 1 upon n. So if this case happens, what happens is that it will be mu to the power n to the power 1 upon n. So this will be mu. But this is not the general case because we know that expectation of x square is not equal to expectation of x whole square. In general, this does not happen. So this is unbiased. We can see from here. So first one is unbiased. Now expectation of 2x bar is what? 2 expectation of x bar. Now again same thing. This is what? 2 mu. So not equal to mu until unless mu is not equal to 0. So here nothing is given, like mu is equal to 0 is not kind of given. So this is not the information. So in general this is also not the one. The next is x1 by n. Now, x1 by n, what I have told you earlier is that x1 is minimum of x1 up to xn. So, it will follow some different kind of distribution. So, it will also not be as unbiased. And if you just want to see that x1 x2 up to xn will have some distribution, so it will have different parameters and this will have some different parameters. Now the last one we are left with this. So expectation of given here is that 2 and plus 1 to the power minus 1. Okay. So it is given here is that 2 and n plus 1 summation I x I up to n. So 2 upon n plus 1 will come, and then this will be what? I x I. So I x I will be what? Uh, Sorry, expectation of this. So it will be 2 upon n plus 1, right? It will be expectation of x1 plus 2x2 up to n xn. Now, one thing we know is that expectation of x1, x2 up to xn all are same, all are mu. So expectation is of xi is mu, right? So then we are left with, we can write it as this 2 upon n plus 1 expectation 1 plus 2 up to n, right? And then xi expectation of xi. So how this is how we can write it. So this is again what summation of 1 plus 2 plus up to n is what? Nn plus 1 by 2, right? So this is n into n plus 1 by 2. Expectation of xi is what? Mu. So this will be cancelled out. It will be mu. So this is what we can say is that unbiased. Right. Now what we want to find is that variance of Tn. So variance of Tn will be what? Uh, expectation of xi is squared minus expectation of x bar or square. So it will be expectation of xi whole square will be what? 2 upon nn plus 1 its whole square as summation I xi whole square minus this expectation. So that one is just mu, right? So this one will be what? This square will come out as a square. So that one will be 4 and a square and plus 1 square. Now a square of this, it's a square. Okay, it's a square will be what? Expectation of xi square, and then its square will be let's say you have 1x1 plus 2x 4x2. So its square is basically what? This one is 1 plus 2 plus this. So this one is cube form of thing. So 1 square plus 2 square up to n square. So in the time of xi square, we have formula like this: 1 square, 2 square up to n square. So its formula is what? Nn plus 1 2n plus 1 divided by 6, right? So it will be cancelled out. Basically, here we have n 4 terms and here we have n 3 terms, right? So it will always happen that one n will be in the denominator. So one n will be in the denominator. So if you have something like this 1 upon n kind of thing, so as n tends to infinity, this goes to 0, right? So this goes to 0 means the variance of Tn goes to 0 as n tends to infinity. So variance of Tn goes to 0 as n tends to infinity, and then it means is that it is consistent operator. So this will be the consistent operator. Okay. Now next question is that you have these observed values of random sample of size 6 from the population having this density function given by this function. Then we want to find the MLE. Now you need to understand this question very carefully because here is one range given: x is greater than theta, that I have told you earlier that this may happen. So what we have here is that f at theta x. So firstly we will find L. So L is what? So it will, this multiplication will go as summation in the power, yes, I from 1 to up to n. So this is from 6. I is equal to 1 to up to 6. Okay, now we can take log, so it will be L small l. So it will be minus summation I is from 1 to up to 6 xi minus theta, right? Now, if we do the differentiation, so del L del theta is equal to 0. So, uh, this is what? This is summation xi minus 6 theta, right? 6 theta, because n times theta. So, it del L del theta is equal to what? Minus 6. So this cannot be is equal to 0, right? So this is what we are getting here is an absurd thing. Okay. So at this point of time, when you get del L del theta as an absurd value, because we in the time of checking L, we do not consider here its range. So now we will consider here its range, and then we say is that we have log L is equal to minus xi plus n theta, and then let me just write it. This is minus summation xi plus n theta. So we say that this is maximized when theta is minimized. Okay, so uh, minimum. So theta will be what? X1. So x1 is the point where it will have the smallest value. So at this point, because if we take anything greater than this, then summation xi may be less than that value, right? So at this point of time, we say x1 will be the order statistics, which I have told you earlier in the time of telling you order statistics, this one. Okay, so these are the order statistics. So x1 is what? Minimum of this order statistics. So this one. Now the minimum of this is what? Minus 9 minus 2. I'm sorry, minus 9 minus 6. So minus 9 is the minimum value. So at this point of time, theta is minus 9. Okay, so this is the point where maximum likelihood function fails, and when it fails, we do the parameter estimation by using the logic. Okay, by using the range, and then we can find the estimator. Okay, so next thing is that we want to find this. Again, MLE. So I have told you earlier that MLE is the most important one. Okay. So now again we have LFX theta. I just want you to do this question with me. Okay, because the chances that this will come is really high, obviously. So this question, just do with me, because we have done enough of the question depending on this MLE function, right? So you can do this question with me. So what we have is that we have PDF here. What we do is that we do firstly find the likelihood function. Now to find the likelihood function L, we do the multiplication, right, over I is equal to 1 to up to n divided by theta square e to the power minus xi by theta. X greater than 0, theta greater than 0. So this is the multiplication. So this one will come as multiplication. Theta square will multiply n times will be theta to the power 2n, and it will be summation in the power, right? So now small l, which is equal to log L, will be what? This uh, multiplication. So log of, let's say we have log of this. This is multiplication xi. So that one will be what? Log x1, x2, xn. Okay. So log x1, x2, xn will be what? Log x1 plus log x2 plus log xn. So it will be summation log xi, right? Now this is in denominator, power is 2n, so it will be 2n log theta. And then its log e will be 0. Sorry, log e will be 1. So this will be minus xi by theta, right? So now the next step is what? We want to find del L del theta. This one is 0. This one will be minus 2n upon theta. And this one will be plus summation xi divided by theta square, right? Now the next step is what? Del L del theta is equal to 0. So minus 2n theta, sorry, 2n upon theta is equal to what? Summation xi by theta square. Now theta is greater than 0, not equal to 0. We can cancel it out, right? Now, so theta is equal to what? Summation xi divided by 2n. Now we have found one estimator of theta. Remember, at this point of time, we have always found one estimator. Not always, but if we have found estimator, it's not necessary that this is the maximum. So then the next step is that we need to find del 2 L del theta 2. So del 2 L del theta 2 will be what? Will be minus 2n upon theta will be what? 2n upon theta square, and then it will be minus 2 summation xi divided by theta cube, right? So we can take 2 by theta square common here. It is n. It is what? Uh, Summation xi upon theta. Now summation xi upon theta is what? 2n. So it will be what? 2 upon theta square. N minus 2n will be what? Minus n. Now 2 is positive, theta square is positive, n is positive. So this one is negative. So this whole is negative. Now it is less than 0 for sure. So now we can say this theta is MLE, maximum likelihood function. So theta will came as xi by 2n, right? So summation xi by 2n will be the answer. So this is maximum likelihood estimation, right? Okay. So now the 10th question we have here is that x1, x2 up to xn with a random sample came from u1 theta population. Theta is greater than 1, and that's why we have this range 1 to theta, right? So which of the following is unbiased estimator? Which of the following is unbiased estimator? So yes, okay. Now this is just given in the time of in the term of x bar. Okay, so this is only in the term of 2x bar, and others are in the term of uh, xn. So expectation of 2x bar minus 1, this is easy to find. Now in the term of u1 theta, x follows u1 theta, mean is what? Mean is a plus b by 2. So 1 plus theta upon 2 is the mean. So 2 expectation of x bar. So expectation of x bar is obviously is equal to expectation of mu. So this is 1 plus theta divided by 2 minus 1. 2 will be cancelled out. It will be 1 plus theta minus 1, which will be theta. So this is the unbiased estimator for u1 theta, right? Unbiased estimator for theta. Now we have found the answer, but then you need to understand how do we check others. So to check others, what we need to find is that expectation of this uh, all. So we can see here is that the common point here is what? Xn, Xn, Xn. So Xn is what? The order statistics maximum. So from here, if I go here, you can see that fxn is this probability of this maximum. So fxn is that if we put n here, sorry, in this place, if we put n in place of r, then we can find it. Right? So that so now for this example, I show you how we can do this. So firstly, I'm gonna write the formula n factorial divided by r minus 1 factorial n minus r factorial, right? Fx, capital Fx to the power r minus 1, 1 minus Fx to the power n minus r, right? So, sorry, so Fx and at x is equal to n factorial. This one will be n minus 1 factorial. This one will be n minus n factorial, so 0 doesn't matter. Now this one is fx, this one is fx all to the power n minus 1. Now 1 minus fx, n minus n will again be 0. So this one will be n fx, f capital X all to the power n minus 1. Now we are doing this for what? Mm, uh, you have u uh, theta minus 1. So let's say this xn is this. So we are just considering y as xn. So, okay. And then we are taking y as yi as xi minus 1. So that we can come with the distribution u 0 comma theta minus 1, because this is like most popular form, like u 0 to 1 is the most popular one, if that one is that standard form. But basically we can just convert it so that this one will come as the standard form, right? So fx is what? And now, if you do in the usual form, then also it is b minus a, 1 upon b minus a. If you like this, then it will be theta minus 1 minus 0. So you can do in either form, right? So n theta minus 1. And then capital Fx is what? Capital Fx is uh, x to the power uh, n minus 1 divided by theta minus 1. So here you get some kind of profit here, because then if you take 1 comma theta, what will happen is that you will have a minus b t minus a, yeah, or whatsoever, sorry. Capital Fx is what? X minus a divided by b minus a. So if you consider a as 1 and then b as theta, what will happen is that you will come out as x minus 1 to the power n minus 1. Then it will be a little bit lengthy to just solve, nothing else. It will not be difficult, that's for sure. So you can take any of them. So this is fxn at x. So this is the PDF of xn, right? So now we want to find the expectation. So if we have found the expectation of it, we can just multiply so to find the expectation of others. So expectation of this x is equal to what? Uh, 0 to theta minus 1. This is the range. and then you have x to the power n minus 1 here, 1x will come from here, so you will have x to the power n. Here you have n. In the below you have theta minus 1 to the power n dx, right? So this is what n upon theta minus 1 to the power n will come out. X to the power n is what? X to the power n plus 1 will be theta minus 1 to the power n plus 1 divided by n plus 1. So it will be n upon n plus 1 theta minus 1, right? So this is the expectation we have. So we can write expectation of n in n plus 1 n yn is equal to theta minus 1, right? So here you can see n plus 1 by n, mostly you have like this yn, or so it's, what happens is that it's plus 1 by n, its expectation is coming out as theta minus 1, so it is not coming out as theta, right? So uh, these are not the unbiased estimator. So this is the continuation of the last question basically. So we want to find the maximum likelihood function from the last question. So the maximum likelihood function from the last question, you have u1 comma theta is sorry, u1 comma theta. So so what happens is that you have log likelihood will be what? Fx is 1 upon theta minus 1, because xi follows what? U 1 comma theta. So this is how fx is given, 1 upon theta minus 1. So L is what? 1 upon theta minus 1 to the power n, right? Now log L will be what? Minus n log theta minus 1. Now again, in if you do del L by del theta, what happens is that n upon theta minus 1. Now if you take it is equal to 0, then that means minus n equal to 0, again illogical. So what happens is that in this case it is minus log L theta minus 1, or you can uh, see it from here. If we take the theta as the maximum value, then L will be the maximum one. Sorry, the largest theta. Then we have the maximum likelihood estimator. So this xm will be the maximum likelihood estimator. So this is how it goes. So if you want to maximize it, you want to, if theta is in denominator, then you need to take the maximum value. If theta is in numerator or in positive value, then you need to take the minimum value. So this is how we solve this kind of question. Now next question is that we have Bernoulli distribution, okay, and then we want to find the unbiased estimator of p times 1 minus p, okay. Now p times 1 minus p, okay, p times 1 minus p, you need to understand is that this is the variance of Bernoulli distribution. So basically, the question is here is that we want to find the unbiased estimator of variance of xi, right? So variance of xi is equal to what? P1 minus P. Now we can consider it as one parameter because here also just P is given. Okay. So now if you just do MLE or any kind of function, theta would come as summation xi upon n, because it is basically what? This is the mean, right? So it will be summation xi minus 1. It will be summation xi minus 1, right? So expectation of theta is equal to what? Uh, Expectation of this value, right? So expectation of summation xi minus n minus summation xi divided by n and its whole square. So basically expectation of uh, so this is what? This is theta. So summation xi upon n will be what? 1 upon n and theta. And this one will be, sorry, this one is given for m values. So m theta. And this one is 1 upon m. And this one for m values, it will come out. But xi square will be theta. Uh, Sorry, this one will come out as just a minute. So in the time of variance, as you have learned, is that variance of x bar is what? Sigma square upon n. So this will go like this. This will be variance of expectation of this is what? Theta. So it is also theta, but it will come as theta upon n, or maybe you can write it as theta 1 upon m square. Here n square, so 1 upon m square will become out. It will m, and expectation of xi square. Expectation of xi square also is theta. So it will come out as theta. So basically at the last we have theta minus theta upon m. So this one is m minus 1 upon m theta, right? Or maybe you should write it as theta cap. So we say is that expectation of m divided by m minus 1 theta cap is equal to theta. So this is basically the parameter estimator. So if you have expectation of something is equal to theta, and theta is what? P1 minus P, right? So m minus 1, m upon m minus 1 theta cap. Theta cap was what? Summation xi. So this is x bar, basically x bar 1 minus x bar. So you have estimator is m upon m minus 1, m upon m minus 1 x bar 1 minus x bar. So this one will be the answer. Uh, Now the next question is that you have okay, so here also all you need to do is that you need to find the MLE. So this is you can do on your own. So I'm gonna go to the next question, and if not done, or maybe we can do the other question in the next class. So whatsoever you suggest. So any suggestions from you? Like, okay, so what we do is that we will do this question here, and then we will left with, I think, 3 4 questions that we can do in the next class. So it will be in the continuation most probably. So we will do for these question firstly, and then we will do the the new ones. So uh, what is given here is that you have given here is 1 upon n summation xi square. Now you need to understand here is that here mu is equal to sigma square is given. Okay, so your density function will be changed here. So now you have x per and you have theta. So theta one parameter you have, you do not have two parameters. Okay, here I under root. So it is what, under root 2 pi sigma. Sigma is root 2 theta, sorry, root theta. So it will come out as under root 2 pi and then root theta will be in the continuation. E to the power minus 1 upon 2 sigma square is theta, and then xi minus theta whole square, right? So now we can do the same thing again. So log of L is what? Minus n upon 2. So this is what? It will be n upon 2. So 2 pi theta n upon 2 simple. So minus n upon 2 log theta minus n upon 2 log 2 pi. We can write it in the same, but just theta, we are going to differentiate with respect to theta. That's why we are separating it in this way. And then it will be minus 2 theta summation xi minus theta whole square, right? So now del L by del theta will be is equal to what? Minus n by 2 theta, right? And then uh, this one will be 0, this one will be plus 1 upon 2 theta square summation xi minus theta whole square, right? So uh, this is for this, and then for the next one it will be minus 1 upon 2 theta, right? And then it will be 2 summation xi minus theta, and then for minus theta it will be plus. So this is the whole del L by del theta, and then we will what we will do is that we will take this value as 0. So now you can see 2 theta, 2 theta, 2 theta we have everywhere. So we can just remove this, and then from here we can write 1 upon theta summation xi theta square, and then this one will be 2 xi minus theta, and then this one will be inequality. So this one will be this uh, minus theta square plus 2 summation xi minus theta is equal to n, right? So 1 upon theta summation xi square plus theta square minus 2 theta xi. From here, if we just open the bracket and then plus, it will be 2 xi, uh, sorry, it will be in the multiplication, so it will be 2 theta xi, and then uh, 2 theta square minus 2 theta square, right? These are all in summation. So this one will cancel out, theta square minus 2 theta square will be minus theta square. Then we can just take theta over there. So it will be theta summation xi square, and then we can write this as n theta square. Now we will use this u is equal to 1 upon n summation xi square. So 1 upon n summation square, we will just divide n by the whole, and then we can write u minus theta square is equal to theta. So it will be theta square plus theta minus u is equal to 0. And and then it will be theta is equal to minus 1 upon 2 plus minus under root 1 plus 4 u upon 2, right? So my now you have uh, minus you have one thing minus 1 by 2 plus 1 plus 4 u upon 2, and then the minus. Now we need to check the condition on the theta. So theta is greater than 0. So if it will be this part, this is not possible, right? So 1 plus 4u is inside, it's good, but this is positive. These all thing will be a negative value. So that means theta is a negative value. So this is not possible. So A will be the answer. Now you need to go through the del 2, del theta 2, and then you need to find whether this thing is. So what we can do is that we can just simply write del L by del theta in terms of u. So I'm just writing it. You can check it later on. So del L del theta is what? N of minus n upon 2 theta plus n upon 2 theta is square u minus theta is square. So it will come out as n upon 2 theta is square u minus theta is square minus theta. So now if we find del 2 del theta 2, it will be n upon 2 theta is square u minus 2 theta minus 1 minus n upon theta cube u minus theta is square minus theta. So now you need to put the value of theta in terms of u, and then you can find whether it is less than or not. So on the basis of this, this will be the empty. Okay, so next we have some questions, but then we can do that in next class. So I'm gonna stop this class at this point. So I hope you have understood the estimation, how we do the estimation, and what are the estimators, how do we check whether it is good or not, and then uh, most of the part related to that. So yeah, I think I'm gonna stop this presentation. Okay. Okay, so thank you for the joining, and then I'm gonna stop the recording, and then okay, thank you everyone for joining, and yeah, net issue audio not working. Can we get the consolidated formula for exam preparation? It is okay. Actually, I'm not the one. I'm just for the problem solving session. So I need to tell you that problem solving session we conduct is different. So we are not gonna formulate the exam paper. So if you have any question regarding this pattern, then you can ask the NPTEL directly. But the questions, like if you do from the assignment or from the things which I'm taking also. So considering this, I think it will be useful for you. So if you just go through all these things, because this is how I make also the assignment, that what are the things which may come in your exam and what are the kind of assignments you need to solve. So I think if you go through like for exam, I have never given the exam of NPTEL. I have done this course, so I know the course things, but I don't know about the exam pattern. So that one you can go through, like NPTEL team. Like I have no idea about that. Okay. Okay. Thank you. Thank you for joining. And okay. Uh, mail ID. Mail ID. I can give you my mail ID, but that's not gonna work. So NPTEL team a mail ID. I don't know. I ask query. You can ask in the forum. There is a NPTEL forum. So maybe if you will ask there, they will reply. So this let me just end this class firstly. So thank you everyone.